Hi, I'm Will Usher, a grad student at the Ski Institute at the University of Utah, and in this talk I'm going to present our work on achieving interactive visualization of Terascale data entirely on the client in the browser. So as a spoiler alert, the answer to this question is that it's fact, if you make the right algorithmic and data compression choices. So first let's take a look at why we'd want to do fully client-side visualization. From a developer standpoint, we can target a single standardized environment, which is cross-platform. So essentially the browser becomes our cross-platform portability layer. Deploying our code through the browser also makes it widely accessible to users, so anyone with a browser and network connection can run it. Specifically for client-side visualization, running our app on the client lets us get low latency interaction. So we're processing the data locally on the client. We don't have to go back and forth to a server. So it will reduce latency that the user has. And it will also let us save money in terms of deployment costs, where we don't need to run expensive backend servers to perform computation. So if we consider a large-scale deployment like the New York Times COVID tracker, if this needed some expensive compute to be run, doing that or paying for that can be quite significant. Prior work has deployed SciVis apps on the client, typically using WebGL for rendering or processing, but these are somewhat limited by the state of the browser ecosystem at this time. So you lose access to native libraries and JavaScript performance is kind of subpar, but the local processing alleviates latency to the user. On the other hand, applications using a remote server for processing can deliver powerful computation, since you have access to pretty much arbitrary compute on the back end, and you can leverage the existing native libraries that you're familiar with on the server, but there can be costs with latency and server costs. So to summarize these challenges in bringing SciVis to the browser, the widely used libraries that we have on native applications are typically unavailable. The performance of JavaScript is not really where we might want it to be. There's no solution for GPGPU. WebGL is really just a rendering API. There's no compute shaders. And WebGL is also kind of lacking features that we want for high performance rendering. However, the browser ecosystem has been evolving, and these issues can actually be addressed by current and upcoming technologies, specifically WebAssembly and WebGPU. WebAssembly is a bytecode format for a VM integrated natively in the browser, and it's almost as fast as native code. Unlike Java applets and Flash, it's embedded natively in the browser, so it's shipping today in the browser and is available. And it's also targetable from multiple languages, so C, C++ can be recompiled with Mscripton, Rust can target it, C#, Go, Swift, quite a few languages. Specifically for client-side applications, though, WebAssembly modules can also achieve much tighter integration with JavaScript, and JavaScript is actually able to access data from the module directly. So the example I show here on the left is a C wrapper that we put over the Lost Tools API so that we can call it from a WebAssembly module in JavaScript. And on the right side, we're calling into that module to load a LIDAR data file. And what I want to highlight is here, where after loading the LIDAR data, our JavaScript code takes a view of a subset of the WebAssembly memory buffer. That's that heap F32 buffer. We take a view at an offset of it that contains the actual loaded point data. So we can just get it without copying. WebGPU is a modern high-performance graphics and compute API for the web, and it's in development by the major browser vendors and is available in preview builds right now, but it's kind of on the way. It's definitely less stable than WebAssembly, which is a released product at this point. But WebGPU supports compute shaders, storage buffers, and storage textures, so it lets us really have powerful GPGPU capabilities in the browser. And you can kind of think of it similar to DirectX 12 and Vulkan, though it's much, much easier to use than those APIs. So we first evaluated WebAssembly and WebGPU versus their native equivalents on a few common SciVis tasks, which I'll discuss briefly before getting to our main contribution. So here we evaluated using native libraries compiled to WebAssembly to load different data formats. So on the left, we're loading TIFF stacks for connectomics data, and on the right, we're loading LIDAR files for LIDAR visualization using loss tools. So the main takeaway here is that these sorts of data file processing tasks on the CPU can be about 2 to 4 times slower than the native equivalents, and these are all run on a Surface Pro 7. We also compared a textbook serial marching cubes implementation in C++, JavaScript, and WebAssembly, and we find that in Firefox, our WebAssembly version is actually just 1.5 times slower, and it's 3.2 times slower in Chrome. And this benchmark is run on a sampling of 100 random isovalues over a range representing kind of common visualizations. We also tested a textbook data parallel marching cubes, where we use prefix sums and stream compactions to find and filter the active voxels and output the vertices. And while we don't see much of a speed up over the serial version on the Surface Pro 7, we do see quite a significant speed up on the RTX 2070, up to 7 times faster than WebAssembly and 5 times faster than native C++ version. The most important thing that I want to mention here, though, is that the performance of WebGPU is on par with the native Vulkan implementation, though we do see some overhead on smaller data sets. Finally, we compared parallel decompression performance on the GPU by porting ZFP's CUDA decompressor to the Vulkan and WebGPU. And we compare this against the CUDA implementation on the RTX 2070, and we have to compare it against the serial CPU implementation on the Surface Pro 7. So obviously CUDA is not available, but ZFP also doesn't support decompression with OpenMP, so we only have the serial one to compare against. While our implementation trails the CUDA one quite a bit, we still find again that Vulkan and WebGPU perform about on par, and even on the Surface Pro 7, we do start seeing improved decompression performance, which is exciting. So hopefully by now you're motivated that WebAssembly and WebGPU can potentially enable real SciVis apps in the browser. And so now I'm going to discuss our GPU-driven isosurface extraction method for block compressed datasets, which we specifically developed for interactive isosurface computation on large volumes in resource-constrained environments like the browser. I'll mention here a very abbreviated summary of prior work on parallel isosurface extraction. Of course, this is a large field, and they cannot possibly cover everything in this short time. So Daikin et al. Presented a GPU-based method leveraging prefix sums and stream compaction using histopyramids to compute the vertices in parallel for each block. And this computational approach of prefix sums and compaction is followed by most existing methods today, though of course today you would now use CUDA for the kernels and something like Thrust or VTKM for your parallel primitives. Schroeder et al. Presented flying edges, which processes the edges in parallel to efficiently output an index triangle mesh instead of a triangle soup. And Liu et al.'s parallel marching blocks block-based work decomposition is kind of similar to our method. Given the 3D volume, they can process blocks of voxels in a thread group, shown in blue, and within each thread group, a thread is assigned a dual cell, which is shown in purple here. So in contrast to our approach, though, they assume that the entire volume can be stored on the GPU in a single 3D texture, and they only use the block decomposition to accelerate computation by skipping unoccupied blocks. Within each block, they perform flying edges. So there are a few observations that motivate our block compressed marching cubes method. First, isosurfaces of interest tend to occupy sparse subsets of the volume, and users frequently explore neighboring isovalues when they're interacting with their dataset. Third, CFP's fixed rate mode can decompress individual 4-cube blocks without decompressing the entire volume. And finally, WebGPU performance is on par with native Vulkan performance, and so offloading a significant work to the GPU will be beneficial. So let's take a look at our algorithm at a high level. Our method works by moving the isosurface computation, decompression, and cache management onto the GPU to parallelize the work. And key to this is our fully GPU-driven LRU cache, which I'm going to discuss in more detail later. So starting from an existing cache, which was used to compute a previous surface, or an empty one if this is the first surface we're computing. We want to compute the isosurface shown in A. The cache contains a growable number of slots within which a decompressed block can be stored, and it's initialized to have some user-specified capacity. In B, we find the blocks that contain the ISO value or are needed to provide neighbor data for those blocks that contain it. In C, we determine which of these blocks are already in the cache and which must be newly decompressed and added. In D, the active blocks are filtered down to just those that will output vertices. In E, we perform a prefix sum and compaction to compute the IDs of those blocks. In F, we compute the offsets that we're going to write each block's vertex data out to. And in G, we compute and output the vertices. So now let's take a look at the key steps of our method in some more detail. Similar to Liu et al., we store the value range for each 4-cube block of data, which we use to tell us if a block potentially contains the isosurface. So that would be these highlighted here. However, since we never store the full decompressed volume, it's not sufficient to decompress just these highlighted blocks because we'd be missing data that we need for the dual grid. What I mean is that block A, shown here, shares vertices with its neighbors B, C, and D on its dual grid, and so we actually need these data from these blocks as well. So instead, to check if a block is active and has to be decompressed, we actually check if the union of it and its neighbors' value ranges contain the ISO value. If it does, then the block has to be decompressed. This test is done independently in parallel for each block, since we pre-compute and store the block value ranges in a single storage buffer ahead of time. So our final block list is actually those shown in B, which we mark in the list M active. Given our previous cache state for computing the yellow surface, we need to decompress and cache any new blocks from this active list to compute the current surface. So in this case, that's just block 8, which I have highlighted here. So let's step through our LRU cache update and see how it works. So each substep's shown here in C, so CI, CII. Each one of these corresponds to one or more GPU kernel dispatches or parallel primitives. And I'll keep the previous cache state here on the left as a reference. So first we increment the age of all the slots in the cache. Next we run a thread for each block that marks whether that block is needed for the current surface that we're computing, and it's in the cache, or whether that surface, that block is needed for the surface and is not in the cache, so we mark it as new. Or if the slot has a block in it, but that block is not required for the current surface, we would mark its slot as available, making it a candidate for eviction. In this case, we don't have any blocks that are going to be evicted. We just have one slot that was already unoccupied and one block which is new. That's block 8. We perform a prefix sum and stream compaction on these two arrays, M available and M new, to get lists of the IDs of the available slots and the blocks. So that's I new is the new block IDs, I avail is the new slot IDs, and we also compact the slot ages, the available slot ages, which we use to perform a sort by key here to get the slots sorted by a decreasing order of age. We then assign each new block that we're going to decompress to a slot in the cache. So I slot tracks for each block which slot it's stored into. So block 8 is stored in slot 6, and S block stores for each slot which block is stored in it. So block 8 is stored in slot 6. We also reset the age and unmark that slot as available. Finally, we decompress the block using our WebGPU ZFP decompression kernel and output it to the slot in the cache. With all the blocks that we need decompressed, we then compute which of those blocks will output vertices. For example, a block might be made active because it's needed to provide data for a neighbor, but it may not actually contain the surface itself. So in this case, only blocks 0, 1, 2, and 5 are actually going to output triangles for the surface. We then compute the output offsets for these blocks. This is done using a thread group local scan to compute the per voxel offsets, but we only save the total number of vertices that will be output by each block and perform the prefix sum over that. We don't ever save or do a global scan on the per voxel offsets. And finally, we output the vertices to the offsets using the block offset as a base and the recomputed thread group scan as the offset for the voxel. We conducted an extensive performance evaluation of our algorithm. We evaluated it on datasets ranging in size from 67 megabytes to 1 terabyte before compression, and in the benchmarks we cover 16 million voxels to 1 billion. We evaluated on both nested and turbulent sheet surfaces, which have different cache behaviors. So nested surfaces are kind of like the skull or the foot. These are like MRI scans, where as the surfaces at lower ISO values contain those at higher ones. Whereas the turbulent sheet surfaces are more like a crumpled sheet that moves, say, from left to right, where the surfaces don't really contain each other, but they occupy neighboring regions of the domain as you move the value up or down, but are not really coherent with each other when you sample randomly. And we evaluate on 3 common user interaction modes, so picking random ISO values to kind of find what's interesting, sweeping the ISO value up or down to explore neighboring ISO values. We run our benchmarks on the Surface Pro 7 with the integrated GPU and a desktop with an RTX 2070. And we find that for most cases we frequently operate in cache and can provide fast recomputation of the surface. As mentioned before, the random ISO value benchmark on the Miranda and DNS is especially tough because they're very cache unfriendly in the structure of the data, and you see that we have a pretty low cache hit rate on those and lower performance as a result. However, on the sweep up and sweep down benchmarks for those, we have pretty good cache hit rates and pretty good performance as well. I'll only briefly touch on rendering performance since we're just rendering a triangle soup, but in all cases we achieve interactive performance across the tests and even on some quite large meshes. I'll wrap up with a roadmap of challenges that we should focus on to make it easier to bring SciVis to the browser. So I hope that as a result of this talk, you're convinced that the browser is becoming a capable platform for powerful SciVis apps, and it's worth considering. In terms of easing deployment and development, a community effort to recompile widely used native libraries to WebAssembly would be great. Bringing stuff like VTK to the browser. And similarly, we need something like VTKM or Thrust providing GPU parallel primitives through WebGPU to make this easily available. Thanks for your attention. The code and supplemental material and paper are online at this URL. If you have questions, you can contact me via email or Twitter. And I'd like to thank the funding sources that supported this work and colleagues who provided data and feedback on it during the process.